Some transformer faults, they just don't announce themselves electrically at first. A slow-developing internal fault can actually generate gas from decomposing oil long before it produces enough of a current imbalance to trip an electrical relay. But that gas has to go somewhere, right? And the bulk source relay is waiting for it. Welcome to The Explainer. Today we're bridging the gap between mechanical and digital engineering to see how we protect multi-million-dollar power transformers by literally listening to what gas bubbles have to tell us.
Think about it. What if a fault doesn't announce itself electrically? We spend a ton of time talking about these lightning-fast digital relays that catch massive electrical short circuits in milliseconds. But what happens when the danger is practically invisible to those high-tech sensors? Some of the most catastrophic transformer failures out there, they don't start with a giant bang. They start with a whisper. Just a slow-developing internal fault generating zero detectable current imbalance.
Just look at how this timeline escalates. It's like a giant puzzle slowly falling into the worst possible place. It starts with just a little localized arcing deep in the winding turns, which could go on for days. The arc is so tiny the electrical relay is totally blind to it. But that heat is vaporizing the surrounding oil. Give it a few hours and you've got combustible gases. Within minutes, that gas accumulates, the pressure spikes, and if you don't catch it, boom. You are looking at an instantaneous tank rupture. We absolutely have to intervene way back at step 2 or 3.
Section 1. Meet the bubble detector, the Buchholz relay. Let's dive right into this and meet our mechanical hero. To catch that creeping, invisible danger, we rely on one of the most tried and true mechanical devices in the entire industry. Simply put, the Buchholz relay is essentially a bubble detector. If you look at the hardware, it sits right in the pipe, connecting the transformer's main tank to its overhead oil expansion tank, which we call the conservator. Now, since gas is naturally lighter than oil, any gas generated inside the main tank is going to want to rise, right? And its only path upward goes directly through the Buchholz relay.
It is brilliantly simple how this works. First, that localized internal arcing heats up the oil. Second, that intense heat actually breaks down the hydrocarbon molecules in the oil, literally generating gas. Third, those gas bubbles float up the pipe and pull in the top chamber of the relay. And finally, as that gas fills the chamber, it pushes the oil out, making the oil level drop. When that happens, a mechanical float switch inside the chamber just drops right along with it. We've literally just translated an electrical failure into a pure physical movement.
Now, people sometimes treat this mechanical protection as just a backup to the fancy electrical differential relays, but no, they cover genuinely different failure modes. Think of electrical protection as the smoke detector in your house. It catches fast, visible fire events instantly. The Buchholz relay, that is your carbon monoxide detector. It catches the slow, invisible danger building up over time that your smoke detector would never notice until it's way too late.
Section 2. 2 stages of protection. Alarm versus trip. Because this relay reads physical conditions, it doesn't just have a simple on-off reaction. It actually scales its response based on how bad the fault inside the tank really is. As you can see, we typically have 2 stages here. Stage 1 is triggered by that slow gas accumulation we were just talking about. The float drops, and you get an alarm. It's basically the transformer saying, hey, something is quietly degrading in here. But let's say there's a massive, sudden internal short circuit. That creates a violent shockwave, causing a rapid surge of oil up the pipe. That physical surge slams into a second mechanism in the relay, triggering stage 2, an instant, direct trip to shut the whole thing down immediately.
And here is a crucial, absolutely crucial warning. Never, ever treat a stage 1 Buchholz alarm as a nuisance. Don't just silence it until it's convenient to go check. Remember that timeline. If you're getting a Buchholz alarm, your transformer oil is actively decomposing right now. It is very often the earliest available warning of a dying asset, showing up way before the electrical protection even knows anything is wrong.
Section 3. Integrating the signals from mechanical to digital. Now, what's really interesting here is figuring out how we get a mechanical float dropping in a pipe of oil to actually talk to a modern high-speed digital network.
Enter the digital brain, the RET615 Transformer Protection and Control Relay. This is the unit watching the transformer 24/7. We already know it does an amazing job analyzing voltages and currents, but it also has to act as the central hub to interpret those physical, mechanical warnings coming from the Buchholz relay.
Okay, so here is how that hardware to software pipeline actually works. When the float switch drops inside the Buchholz, it closes a very simple electrical contact. We wire that contact right into the back of the RET615 as a binary input. Just a simple 1 or 0, on or off. Then, inside the relay's software, that binary signal gets handed to a specific logic block called map-gap APC. That stands for multi-purpose protection. Basically, map-gap APC translates that raw mechanical trigger into a standardized digital signal the rest of the relay can actually understand.
And this setup right here, it unifies the whole shebang. By pulling that mechanical Buchholz signal into the RET615 through the MAP-GAPC block, we completely avoid having separate, messy, siloed alarm systems. Instead, if the transformer trips, everything goes into one single coherent event log with precise timestamps. You know exactly what happened and in the exact order it happened.
Section 4. The complete protection picture. Let's look at how we bring all of this together now to show how we wrap the transformer in a truly impenetrable web of defense.
Here is our unified defense strategy in action. You've got your TR to PTDF differential protection, that's your high-speed guard for sudden internal faults. Then you have your overcurrent protection, the PHL-PTOC and PHH-PTOC, watching for sustained external overloads. And right alongside them, seamlessly integrated via that map-gap MPC block, is your Buchholz mechanical protection, catching those slow, invisible gas buildups. Every single one of these covers a genuinely different failure mode, but they all work together as one cohesive team, converging on a single master trip gate to save the asset.
So, to wrap up today's explainer, I want you to imagine this. You are the maintenance engineer on call. It's 2 a.m., you get a stage 1 Buchholz alarm, but absolutely none of your electrical protection is tripped. Do you dismiss it? Well, knowing what we know now about the invisible, creeping danger of decomposing oil, ignoring that alarm is literally like unplugging the carbon monoxide detector in your house while everyone is sleeping. The gas bubbles are trying to tell you a story. Will you listen before it's too late? Thanks so much for joining me on The Explainer today. Keep learning, and I'll see you on the next one.